Today we will study about instruction formats and addressing modes. When we talk of a format of an instruction in a computer, there may be various ways, various formats that an instruction can have. An instruction will have a part which will represent the operation part, and then it will or may have an address, and in some computers an instruction may have three addresses. In some it may be two or one or zero, or a combination of some formats. So it will be of these categories, the format of an instruction, and the addresses that are there may be of certain memory location, or they may represent certain register also, uh, that way. So we can take up an example here to see how these formats will be there. And let us say we have to perform, the computer has to perform this operation, arithmetic operation. So a plus b and c plus d, and the answers there have to be multiplied. And if the computer has to do this, and if the computer is using a three address instruction format, it will use these instructions to perform this operation. And each of these instructions will have three addresses. So there will be an operation code here and an operation part, then three addresses. So how will it happen? Say R represents the registers inside the CPU. And so this is R1 register. And what I have to do, first of all, I have to add A and B. A is in memory and B is also in memory. Right? So we have to go to the memory at A position, and there we will find the one of the operands. Then that is to be added to this second operand. Answer is to be stored in R1. So for doing this, uh, this instruction will be executed. Add R1 comma A comma B. Fine. And then we have to do the same for C and D. So take C and D from memory, and then the answer, add them up, and the answer stored in R2 register of the CPU. Then uh, both the answers are to be multiplied. So R1 and R2 is to be multiplied, and the answer is to be stored back to the memory at some location, for example X. So this will be like this: MUL, then X, R1 comma R2. So when we perform this operation on a computer that uses three address instruction format, the program will be like this. Fine. And the advantage of this is clear, that the program will be smaller in size. In this format, the three address instruction format, the program will be smaller in size, but obviously each instruction will be carrying many bits in it. Fine. Bits for this, then for this, and for this. So the size of each instruction will be large. Then there is another, that is two address instruction. If a computer uses this thing, and then the same operation can be performed like this. Then the first operand A will be moved to one register. Fine. Because this is two address instructions, you cannot keep three here. So when we write move R1 comma A, it means A is to be copied to R1, register. Then we can directly use add, where R1 comma B. This means that B is to be added to the contents of R1 and the answer is to be stored in R1. So this operation will be performed. Then for C and D, we will do a similar thing. First bring C into R2, then add R2 comma D, means the D will be added to the contents of R2 and the answer will be stored in R2. And now we have A plus B is in R1 and C plus D is in R2. We just have to multiply them and store the answer in R1, which can be done by this. Then finally we have the answer in R1 that can be stored in some memory location by this. So this is the way the code will be there, the program will be there in a 2 address instruction format. And if we have the same example and we want to do it in 1 address instruction format, then this will be the program. Then load will be there in instruction. When we write load A, what will happen? The A operand will be loaded and it will by default it is there that this will be loaded into accumulator. So this 1 address instruction is an accumulator centric format. So in a computer where the central thing is the accumulator and everything goes to the accumulator, this can be easily implemented there. We just write load A, so A goes into accumulator, then add B means B will be added to the accumulator and the answer will be stored in B, this thing. Then once we have added A and B, and we cannot load C now because it will overwrite accumulator. We need to store the contents of accumulator in memory. So first we need to store at some, for example, T location in memory, the contents of accumulator, that is A plus B. Then we have C and D. So first we will load C, then add D to the accumulator and this thing will happen. Then we have C plus D in accumulator and A plus B at location T. So now I need to write MULT, which means the contents of accumulator, that is C plus D is multiplied by this thing. What is here? It is A plus B. So the answer will be stored in accumulator. And finally, the final answer we can store at any location in memory, for example, X. There is another category which we call as 0 address instructions. These types of instructions are specific uh, to are generally used in those computers which have a stack organized way of executing programs. So there is a part of memory which has a stack in it. So the CPU puts everything on the stack and then performs the operation. So it does not communicate with the registers here. What it does, in this type of computer there will be a stack, and on that stack, we know a stack is a type of memory which is a memory which we use in a stack manner, that is in last in first out manner. So whatever goes last into the stack, that is the first thing that comes out. So it is a LIFO way of doing things. And in this thing, what is done, that when we have to, for example, add 2 operands, one operand is to be put on the stack, then the second is put on the stack, then we perform the add operation, which means that pop the top 2 elements of the stack and add them. And so whenever there is an add, a subtract, or any operation, that means just pop the top 2 elements of the stack, add them, multiply them, and then store the answer back to the stack. So this is how it works. And when we say zero address instruction, it means that the actual operation, the computational instruction, that is add, multiply, subtract, they will not have any address. Right? So here you can see add, it has no address, add no address, mul, multiply, no address. So that is why it is called a zero address instruction. And for executing a zero address instruction on an arithmetic calculation, for example, this must first be put in postfix as a postfix expression. And this must be converted to a postfix expression, then only this thing can be done. So postfix means this will become AB plus CD plus and then a multiply. So what we also call, that is also called a reverse Polish notation. And we can see here, since we have to do A and B addition, so first A will be pushed on stack, then B will be pushed on the stack. TOS means top of stack. So A is pushed on the top of stack, B is pushed above it, then add is written with no address. This automatically means that pop the top two elements, that is this A and B, from the stack and perform this operation on them. Right? Then the answer, store it onto the stack, top of stack. So this is done. Fine. Then we push C onto the top of stack, then push D on the top of stack, then do the add. So C plus D will be on the top of stack now. Right? Earlier A plus B was there, now above that there will be C plus D. So we now need to just multiply this and this. So we just write MUL. So the top two elements of the stack, that is this and this, will be multiplied and the answer will be stored again to the top of stack. And lastly, the answer is there, we just have to store it in memory. We just use pop for that. Pop, and the top of stack, that is the answer, will be stored in memory at a certain location X. And these instructions push and pop are very specific to this computer where there is a stack organization of which uses stack organization and not register organization. So these were the instruction formats. And now if we want to perform the same operation on a RISC computer, so RISC means reduced instruction set computer. So a computer which has a reduced instruction set, that is the number of instructions in it are limited, very few instructions. The manufacturer has kept very few instructions for the computer. Whatever is to be done with these instructions. And this instruction this RISC computer will use these type of instructions to do the same operation. And RISC computers usually have a combination of various things. For example, for communicating with the memory, that is load and store, it will have a two address format. And for the performing the computational operation, it will have a three address format. So in RISC computer, load will be done, that is A will be moved to R1. Fine. Then load will be again done, then the second number will be moved to R2, then third will be moved to R3, fourth to R4. Fine. Now R1 and R2 is to be added, then the answer stored in R1. Then R3 and R4 is to be added, answer stored in R3, overwritten to R3. Then finally R1 and R3 will be multiplied and the answer may be put to R1. And finally the answer is in R1, that may be stored in the memory by using store. This way it can be done. Let us move to another topic, that is addressing modes. So a computer may use one or more addressing modes. We know that an instruction contains opcode, and then it contains an address. So what type of address it will have there? What are the various modes that an address can represent? That is what is called an addressing mode. Right? So if a computer has a instruction, there is an opcode, fine. Then after that opcode, there is some address. What type of address is that? What does that specify? That is what we call as addressing mode. For example, the addressing mode can be implied mode. Implied mode means that there will be no address after that opcode. The opcode will have no address. For example, we have an instruction complement accumulator. We write complement. It is default that complement means we have to complement the accumulator. So the complement instruction will have just the complement opcode and nothing else. So this is an implied mode where there is no address in the instruction. And we just saw the zero address instructions. They are also in this category because they just have an operation there and no address. The addressing mode can be immediate mode. That is, instead of the address, just next to the operation code, there will be the operand. So immediate mode means within the instruction itself, we have the operand. We don't have any address there. We have the operand. Right? So these are the first two modes. In these first two modes, there is no address. In first, there is absolutely no address, no operand. In second, there is no address, but at that place there is the operand. Third is the register mode. Register mode means that the operand is in a register, and that register is specified in the instruction. So the instruction, after that opcode, there will be certain bits which will represent a register, which will show us a register, point to a register, and in that register there will be the operand. Another is register indirect mode, which means that within the instruction will be pointing to a register, and in that register there will be an address. That address will be of the operand. So the instruction will give us an register. We will go to that register. At the register, we will not find an operand, but we will find an address. That address will be the memory address of the operand. This final address, actual address, we also call as effective address. Another fifth one is auto increment and auto decrement mode. This 5 is same as 4. The only difference is that once the register is accessed, it gets auto incremented. So if this register indirect mode is giving us a certain register, we go to that register. If 50 is written in that register, that is the data is at location 50. So after accessing that data at the operand, it becomes 51. This is auto increment. Or when we go to that register, if 50 is written there, it is decremented. It becomes 49. So the data is at 49. It has an auto increment and auto decrement concept there. Otherwise, it is the same as this thing. The sixth one is the direct address mode. That is, the instruction contains an address, and that address is the address of the operand. So in the instruction, there will be some opcode followed by certain address. That address will be the address of the operand in memory. Indirect address mode, number 7. It means that the instruction will have an address. When we go to that address, there we find another address, which is the actual address of the operand. So this is indirect. The address given by the instruction points to a place in memory where we find the actual address of the operand, the effective address. Number 8 is relative address mode. Relative address mode is a mode in which the contents of program counter PC are added to the address part of instruction to get the effective address. That is why it is called relative. So whatever address the instruction gives, that is to be added to the program counter to get the effective address. So if the program counter currently is executing, for example, it is containing 50, so and the next will be 51. This 51 is to be added to the address of the instruction. Say for example the address is 200, so 51 is to be added to 200, then the actual effective address can be reached. Ninth is indexed addressing mode. This addressing mode is used for purposes like, for example, we have an array. So an array may be of length 10, for example. The starting point is fixed, and then we may get an index to next positions. So indexed addressing mode is where the address in the instruction is added to the contents of an index register. Many computers use a register in the CPU called an index register. So the address is to be added to that index register to get the effective address. So for example, the address is 200. It implies that the array is starting at 200. Then we will have an index register which may store 1. So when we which may initially store 1 or 0, which means that 200 plus 0. So the first array element is at 200. Then next time it may be incremented and the index register becomes 1. So the address becomes 200 plus 1. So the next array element is at 201. So this way it can be used. And the 10th one, the last one, is base register addressing mode. Again here there in the computer there will be a base register, a register which contains the base address, and that contents of that register will be added to the address of the instruction. So that contents of this register, base register, will be added to the instruction address to get the effective address. This may be used for things like we have a function, for example. So a certain function or a procedure is stored somewhere in memory. For example, it starts from 700 in memory. So the base register will contain 700, implying that the function is starting at 700. Then the instruction address will give us a certain number. For example, if it says 7, so to the base address, that is 700, 7 will be added. That means we are going to the 7th instruction in that 7th or 8th instruction in that 8th instruction in that function. So this is the base register addressing mode. To we can take a numerical example which will give us an elaborative way of understanding all these modes. Say for example, we have a question here. It says that this is given. So the question is saying that this is memory and this is the address of memory, and it is saying that at address 200 there is an instruction, right? In fact, the instruction starts at 200 and ends at 201. So this is a single instruction. This is the operation code, the op code, what is to be done. Then there is certain bits, there are certain bits which tell what mode of operation is to be done, what is the mode of addressing. Fine, this will tell us what is the mode of addressing, and then there is the address part. So the format is an opcode, then an addressing mode bits, then the address. And it is also given that the program counter register contains 200, and a register XR, which represents the index register, it contains 100. Another register R1 contains 400, and there is an accumulator also. So this is our question, and we have to find what will be the effective address and the content of AC for each addressing mode. So the first addressing mode is the implied addressing mode. There we know that we don't have any address, and then we can go to next. We can see this direct addressing mode. So what will be the effective address in the direct addressing mode? If we see the instruction here, it shows address is 500. So if the address is 500, in the direct mode, we know that this 500 of the instruction means the effective address. So this 500 will be the effective address. So the operand will be at 500. What will be the content of AC? So when the fetching will happen, the fetching of operand will happen. So where is the operand? At 500. So here at 500, the operand is 800. So 800 will be moved to accumulator, fetch it to the accumulator. Fine. Uh, immediate operand way, the immediate operand mode. So immediate operand mode we know means that there is no address in the instruction. Instead, at the address place there is the operand. It's immediate. The operand is immediately there inside the instruction. So this 500 will be the operand. So the operand will be 500, which will move to accumulator. Fine. This is the immediate thing, immediate operand mode. And if we move to this what will be the effective address of that? That will be 201, because the operand is here 201. So we can write the effective address is 201. If we move to indirect address means that go to this place 500. There you won't find an operand, but you will find the address of operand. So this is the effective address when it comes to indirect addressing mode. So 800 will be the effective address. And what is the operand? Go to 800. You will find 300 here. So this is the operand. So the operand is 300. Next, relative address mode. What is relative mode? Where relative mode is one where the PC, the next address, the address of the next instruction is to be added to the address. Right? So PC contains 200. Next instruction will be at 202. So 202 will be added to 500. So we will get 702. That is why the effective address will be 702. And when we go to 702, it is 325. So the operand will be 325. Right? So why didn't we say it is 201? Why we said that the next instruction is at 202? Because it is shown here at 200 and 201 is the first instruction. Next instruction is at 202. Right? So one instruction is at two locations. That is why we have to move two steps. 202 is the next thing, plus 500 gives 702. If it is indexed address, in indexed address mode, we know we have to add the index register contents to the address. So 500 plus 100 means 600. So 600 will be the effective address. And what is at 600? It is 900. So the operand will be 900. What about register mode? In the register mode, this the contents of the register will be taken in. Fine. So the address is not, we don't go to memory here. So we don't go to memory here. Fine. No effective address. And the operand is directly in the register. So here we have a certain register. So we can say that this is the register where there is the operand, and it can be 400, this thing. Next is register indirect, which means that the we go to register, 400 is written there, but this 400 is not the operand, it is the address of operand. So then we go to 400 in memory, we find 700, so the operand is 700. Address is 400 and the operand is 700. What about auto increment mode? Auto increment will be same. We go to 400, there we find 700, and after that there will be an increment. And auto decrement, first there will be a decrement in the register, so 399, then we go to 399 and find the operand there, that is 450. So through this example you can get a better idea of what these addressing modes are and how do they work.